Okay, hello. Thanks for coming. So today we will finish the discussion on basic counting. We have lots of examples, but I will I will go through them very quickly. If you want to know about the details, please check the OCW recording. In this problem, we are going to find out how many ways that we can arrange the letters in the word success to form a string of 7 characters. So we are going to use every one of them and how many different combinations that we can form. So for instance, because there are 7 characters, it seems that each of the character can be selected as the first one, each of the character can be selected as the second one, and so on and so forth. So in that sense, we should have 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 7 factorial ways of arranging the characters. But however, the characters here are not all different. So some of them are the same as each other. So we have 3 S's and then 2 C's. So in that sense, we are going to overcount. But luckily, the overcount ways is very symmetric. So we can do something to the 7 factorial and then obtain the result that we want. Because there are 3 C's, because there are 2 C's, so in that sense, if they are distinct, then we will be counting 7 factorial ways. But if they are not distinct, they are the same, then in that case, the 2 C's, no matter how they arrange one before the other or one after the other, they should be counted in the same way. So we have overcounted 2 times in total. So we should divide the 7 factorial by 2 factorial to rectify the count. And furthermore, the 3 S's, they are also not distinct. So in that case, no matter how these 3 S's are arranged within the word in any order, they should be counted in the same way if the remaining parts are the same. So in that sense, we should further divide the result by 3 factorial. So it turns out that the value is what we want is 7 factorial divided by 2 factorial, and then we get this value and further divided by 3 factorial. Or you can think of it as 7 factorial on top and divided by 2 factorial, 3 factorial at the bottom in an expression. So in general, if we have n objects to arrange, but then out of these n objects, they are of different types. Some of them are type 1, some of them are type 2, and some of them are type k. And there are n1 of them type 1, n2 of them type 2, nk of them type k. Then the number of ways that we can make an arrangement using all these objects is n factorial is they are all distinct, but then we should divide it by n1 factorial, n2 factorial up to nk factorial. Now notice that in the previous case, it is 7 factorial divided by 2 factorial, 3 factorial. We can also divide it by further by 1 factorial due to this u and 1 factorial due to this e. So we get 7 factorial divided by 2 factorial, 3 factorial, 1 factorial, 1 factorial. Okay, now this is another example to test our understanding. We have 5 dashes and then 8 dots. So how many different ways to arrange them? So the answer is very easy because there are 13 objects to arrange, but then 5 of them are the same, 8 of them are the same. So it is going to be 13 factorial divided by 5 factorial, 8 factorial. But now, suppose that we can only use 7 of them rather than using all the 13 of them. So how many different arrangements are there? So for instance, we have 8 dots, right? So the 7 symbols could be all dots. So we can have an arrangement with 7 dots. We can have an arrangement with 6 dots and 1 dashes. So that in that case, there are going to be 7 of them, and so on and so forth. Now to compute or to calculate the number of ways to do the arrangement here, we don't have a single formula to do so. But we can easily solve this by using the rule of thumb, because we can separate the cases by looking at what are the different ways that we can choose the 7 symbols. So the 7 symbols can be all dots, can be 6 dots, 1 dash, can be 5 dots, 2 dash, and so on and so forth, up to 2 dots and 5 dashes. So in that case, for each of these particular case, it is a problem of arrangement with indistinguishable object. And then we can add up the count for each of these subcases, and then we get the result. So we are using rule of thumb to help us. And then this is another example. This is a very interesting example. We want to show this number k factorial is divisible by this term. This term is what? This term is we have a lot of k factorial multiplying together. So there are many of them. There are k minus 1 factorial of them multiplying to each other. So we want to show that k factorial, this large number, is divisible by this smaller number. In order to show this, if you want to use algebra, then it is much harder than if we can argue things using a combinatorial way. If you can somehow relate the expression of k factorial divided by k factorial into some counting problem, then in that case, we can argue that this is a count value, and a count value has to be an integer. So in that case, we can say this one divided by this one corresponds to the number of ways of doing something, so it must be an integer value. Okay, so here we have some example when we plug in the values of k is equal to 3, what will happen? And in general, we want to show that for any positive k, this is true. Try to write down and see if you can interpret the expression by yourself first. And if you do not get luck to find out the reason, please visit the OCW recording for details. Okay, we now look at a slightly different way, of a counting problem. So this time we have n distinct objects, so n types of objects, and then each one of them has unlimited supply. And then we want to find out how many R permutations that we can form. So how many ways that we can make an arrangement with R objects, and then so this is the R permutation. So the answer is very simple, because we are going to select R objects in total, and the ordering is important. So we look at the rule of product. So how many ways to pick the first object? So because there are n types, so we have n choice for the first object, and then another n choice for the second object, and then another n choice for the third object, and so on and so forth. So in that case, the total number of ways to do the arrangement is n to the power r. This is fairly simple, right? So we have two examples here. The first one is we want to count the number of integers that are between 1 and 10 to the power 10, such that they have a digit 1 inside. And then this one is actually not easy to compute directly. So there is actually another hint. So let's try to do this case first. How many of them do not have 1 inside? So first of all, any number between 1 to 10 to the power 10, except the last one, okay? You can think of them as a 10 digits number. So 1 is you start with 9 zeros followed by a 1. 2 is you start with 9 0 followed by a 2, and so on and so forth. And 10 to the power 10 minus 1 is 9. Okay, so there are 10 nines together. So somehow these numbers, you can try to view them as a 10 digits identity, or a 10 digits number. Then in that case, because we are adding zeros to the front, so it will not change the number of ones inside. So if we want to count how many of them doesn't have 1 and how many of them contains a 1, then the two ways that we view the number will be similar. And by doing this transformation in how we view a number, then something will become very easy. If you want to count how many of them do not contain a digit 1 inside, then we know that for every position, we should not see a 1. So every position, there are 9 choices only that we can do. So in particular, there are 9 to the power 10 ways of selecting a number that doesn't have a 1. And based on this, and do some careful counting, we should be able to count what is the value that we require for these two answers. Okay, I will leave this for you to try. Another exercise is this time we look at bit strings. So bit strings is a string that has, for each position, it is either 0 or 1. So we call this a bit. So in CS, computer science, it is natural to consider bit strings. And how many of them, how many of the bit strings of length n are there? So we will see that because for each position, there are 2 choices, so the number of bit strings of length n will be 2 to the power n. But when we want to count the number of ways to get a bit string with length n that has even number of zeros, then it turns out that half of them has even number of zeros and half of them doesn't. So in that case, how we can argue why this is true? You can solve this by using a combinatorial argument. Okay. And then the next way is this time we are going to look at the formula for CNR. We know what is PNR already. So PNR is n times n minus 1 times n minus 2. Altogether, they are R terms multiplying to each other. And earlier, we have shown that PNR is equal to PRR multiplied with CNR. So this is shown by a combinatorial argument. So in that sense, CNR is equal to PNR divided by PRR. So it is CNR is equal to, so this part is PNR. So this is n to the power R falling, the falling power of n to the power R, divided by R to the power R, the falling power, so which is R factorial. So this is Cn, okay, so this is like this. And alternatively, we can add more terms to the numerator and add more terms to the denominator. So in particular, we can multiply the remaining terms to make, so we can try to make the numerator to be a better looking term, making it into n factorial. So the missing terms will be n minus r minus 1, and so on and so forth up to 1. So we are missing n minus r factorial in the numerator. So by multiplying n minus r factorial at the numerator and the denominator, we will get n factorial in the top, and then r factorial n minus r factorial at the bottom. So this is an alternative expression for CNR. But then I would recommend you to remember the first one, because the first one is much more general than the second one. So for the first one, we can also define CNR term, binomial term, for general case where n is not an integer. As long as r is a positive or non-negative integer, we can try to plug in different values of n. So let's say n is equal to 1.1. So we can have 1.1 choose 3. So in that case, it is 1.1 times 0.1 times, I don't know what it is. So it is times this one minus 1, right? Yeah, so somehow some value minus 0.9, something like this, divided by 3 factorial. So we can define things when n is not an integer. But for the latter one, then it is not easy, okay? So the first one makes sense. It is n to the power r falling divided by r to the power r falling, okay? Now, but for the second expression, it is also interesting. So you will see that by plugging r as n minus r, this term will switch. This becomes r factorial, and this becomes n minus r factorial. So we can immediately see that CNR has to be equal to Cn n minus r. But we have already known this because we can show this by using a combinatorial argument. But anyway, This is a good thing to notice. An example here. This is a very interesting example. Not easy to find out the correct answers for every question here. So we have a hexagon. Okay, we have a hexagon here, and then we want to ask for this hexagon. Oh, okay, we are going to draw diagonals among the vertices. So we have a hexagon, and then there are diagonals. We claim that, so not we claim, we assume that no three diagonals meet at one point. So it is not that regular in shape. Otherwise, this diagonal, and this diagonal will meet at the same point. So here we are switching moving the positions of these vertices slightly so that no three diagonals meet at one point. We want to find out how many diagonals are there. So in order to find out the diagonals, it is rather easy because we will see that for every two vertex in this polygon, in this hexagon, there is an edge. So how many edges are there? So there are going to be 6 choose 2 altogether, 6 choose 2 edges. But then 6 of them are the outer boundary of this polygon. So in that case, it is going to be the number of diagonals will be 6 choose 2 minus 6. Is that okay? But now we want to ask how many intersections between the diagonals we can find. Now this is now not that easy. Oh, it looks like that because we have, let's say, 6 choose 2 edges, and every 2 edge will have an intersection. Then in that case, it is 6 choose 2 and then choose 2. But then, first of all, 6 choose 2 is not the number of diagonals that we have. And also, some diagonals do not meet. So for instance, this diagonal and this diagonal do not meet inside the polygon. So in that case, it is not every 2 edges will meet at one point inside the polygon. So in order to get a certain intersection inside the polygon, so how can we do? So for this intersection is formed by this diagonal and this diagonal. So an intersection corresponds to two crossing diagonal. But when we have two crossing diagonal, that means that we are choosing 4 outermost vertex. If I choose this 4, I will have this intersection. If I choose this 4, I will have this intersection. Is that okay? So for any way that we are choosing 4 outer vertex, it will give us an intersection. On the other hand, for each intersection like this, it corresponds to 4 outer vertex. Is that okay? So the number of intersections will be equal to 6 choose 4. And finally, this is the hardest question. So we want to find out how many line segments are there when these diagonals are formed. So the line segments will be formed when we consider the intersections between the diagonals. So for instance, originally this is a single diagonal, but because of these intersections, so it is this whole diagonal is separated into 5 little parts. So 5 line segments. So this one part, another one, another one, another one, and then another one. So how many line segments will the diagonals formed by the intersection points? So I will leave this for you to think. So the idea here is that by knowing the number of diagonals and knowing the number of intersection points formed by the diagonals, we have these two values, we can calculate directly the answer of the third one. So if you are okay with this question, yes, try to generalize it so that we are talking about a hexagon here. So how about an n-sided polygon with the same setting? So what will be the answer for the 3 questions below? And next one here is how many ways that we can select 3 numbers from 1 to 300 such that the sum is a multiple of 3. So for this question, we look at multiple of 3. So naturally, we should separate the 300 numbers into 3 groups. each one of the group will have the numbers such that after division by 3, they have the same remainder. So we are grouping, so 1 up to 300, we are grouping all the multiples of 3 together in one group, and grouping all the multiples of 3 plus 1 into another group, and grouping all the multiples of 3 plus 2 into another group. So there are 3 groups, and in this case, 100 numbers in each group. In order to select 3 numbers such that the sum is a multiple of 3, there are not many different choices that we can do. One way is we are selecting 3 numbers from the same group. Or an alternative way is we are selecting 1 number from each group. So selecting 3 numbers from a particular group, there are 103 ways. And then there are three ways that we can consider. So we are selecting 3 numbers from group 0. Let's say they are representing the multiples of 3, because I call it group 0 because when divided by 3, any number will have remainder 0. Okay. So also we can select 3 numbers from group 1. So there are 103 ways. And then also 3 numbers from group 2. So there are also 103 ways. And then there is one more way. You can select 1 number each from each of these groups. So we select 1 number from group 0, 1 number from group 1, and 1 number from group 2. And there are 100 choices each. So we have 100 to the power 3. Now for this problem, if you really understand what is going on, try to change number a little bit. For instance, let's say how about selecting 4 numbers from 1 to 200 such that it is a multiple of 3, or selecting 3 numbers from 1 to 205 such that it is a multiple of 4, something like this. So this will check your understanding whether you have really mastered the idea of this type of problem. Another question here is we have 5 pirates. They have a treasure box. They put the treasure box in a locked room, but then to ensure that nobody is going to open the locked room secretly, they agree that this locked room should be opened only when 3 or more pirates are present, so more than or equal to half of the number of pirates are there. So any 2 pirates should not be able to open the locked room, but then any 3 should be able to open the locked room. So in that case, they need to design some locks and some keys. So we will need to have a certain number of locks put on this locked room, and then every one of them will have some keys, but then any 2 of them should not have a full collection of the keys, but then any 3 of them should have. Then in that case, how should they design the lock system? In the lecture, we are presenting this problem in a slightly different way. We talk about the Star Wars problem. So watch the OCW recording, see if you understand the Star Wars problem, and then if you are okay with that, then this is going to be the same problem as that one. Okay, this time we have a different problem. So previously we talked about there are different types of objects with unlimited supply, and then we are talking about how many ways can we do the arrangement. But now we changed the setting a little bit. We still have n types of objects, each with unlimited supply, but then we are asking how many combinations are there. So we do not require the ordering to be important. So we just want to know, okay, so for instance, let's say there are 3 types of objects. Let's say we have the sun, the moon, and the star. And then we want to pick 5 of them. So how many ways can we do so? Maybe we are picking 5 suns, we are picking 5 moons, maybe 2 suns and 3 moons, but we don't care the ordering. So 2 suns and 3 moons is the same as sun, moon, sun, sun, moon, or moon, sun, sun, moon, sun, something like this. We don't care about the ordering. So how many ways, how many R combinations are there? It turns out that the answer can be simplified or can be captured by a combinatorial term. see n minus 1 plus r, choose r. So why? Why is it correct? Okay, remember we have n distinct types of objects, so we can somehow think of them as we have n boxes. Okay, and then we want to get an R combination, so we are selecting only R objects in total. So let's imagine that we have exactly R balls. Now we are going to put the R balls into the boxes. So a particular way to put the R balls into the boxes will give us a certain combination. So here, this combination says I'm going to select 2 objects from type 1, 1 object from type 2, and 3 objects of type n, and so on. Okay, so as long as we can count how many ways that we can distribute R balls into the n boxes, we are done, because there is a way, a one-to-one correspondence between R combination here and R ball distribution here. Okay, now further, okay, so this time, so we now focus on how to count the number of distribution of R balls into n boxes. What we are going to do here is we use the very clever representation. This representation is we use, let's say, we use a star to represent a ball. So here we have, and then we use a bar to represent the separation between the boxes. So when there are 5 boxes, we have 4 separations in between. And then the stars are counting how many balls are put into the corresponding box. So box 1 has 2. So I write down 2 stars, and then we see a separation. And then box 2 has 1 ball, so I write a star, and then a separation. This separation is separating box 2 and box 3. Box 3 doesn't have anything, so we have another separation, and then another separation. And finally, these 3 stars represent that we are going to put 3 balls into box 5. Okay, so this representation tells us a particular way of putting our balls into these n boxes. But on the other hand, any representation with exactly n minus 1 bars and then r stars will be corresponding to a way of distribution of our balls here. So in that sense, what does that mean? It means that as long as we can count how many ways that we can arrange n minus 1 bars and r stars, then we can get the count of how many ways to put r balls into n boxes. How many ways are there? There are n minus 1 bars, r balls, or r stars. So altogether, the total length is n minus 1 plus r. And then we need to select which positions to put the balls. So choose R. So that's it. Okay. Okay, so altogether, these represent the bars, this represent the stars, and then the total length is n minus 1 plus r, and then we need to choose which position we want to get the star. So choose R. Okay. So there are a couple of questions for you to try. In particular, this is usually a standard question. So how many solutions, how many integral solutions? I want x, y, z to be integer, actually to be non-negative integer. We want to make sure x, y, z, they are non-negative integers, okay? Such that x plus y plus z is equal to 11. Okay, this is the same as how many ways that we can put 11 balls into 3 boxes. The plus here actually represents a separation. So the total number of ways to do so is 11 plus 2, which is 13, choose 11. Okay, so this is the answer for exercise 2. And for exercise 3, it is the same setting as exercise 2, except that we require that x, y, z, they are positive integers. So in such a case, we know that there must be at least a ball in x, at least a ball in y, at least a ball in z. So instead of doing the counting like this, we ask how many extra balls that we should put in the first box, how many extra balls that we should put into the second one, and how many extra that we should put into the third one. The total number of these extra balls is equal to 8, because we put one ball here, one ball here, one ball here originally. So how many ways that we can have? If we look at the extra balls, let's call it x prime, y prime, and z prime. So how many non-negative integer solution, x prime, y prime, z prime, such that x prime plus y prime plus z prime is equal to 8. And then we get back to the same type of problem that we know how to solve. So this is how we can solve exercise 3. Okay, finally, let me present you some of the interesting identities using these combination terms. So the first one we have actually talked about earlier, I guess. If not, then let's do so now. We claim that CNR, n choose R, is always the same as Cn minus 1R plus Cn minus 1 R minus 1. So this is called the Pascal identity, discovered by the French mathematician Pascal, but actually it is also known in earlier Chinese kingdom in the long time ago. Why is it correct? Okay, so we don't need to know the expression, the formula for CNR to solve this. We can argue this by using combinatorial arguments, totally by logic. Okay, so CNR is the number of ways to pick R objects out of N. But then we can look at a particular object. Let's say the first object, we mark it as very special. Okay. In a way to select R objects, there are two cases. One is we are selecting this special object, or we are not selecting this special object. So if we are not selecting the special object, that means that all the R objects are from the remaining n-1 objects, so we get this term. On the other hand, if we must include the special object, then we need to select R-1 extra object, and these extra objects are selected from n-1 remaining object. So in that case, we have this term. Rule of sum tells us that adding up will get the correct corresponding result. So this is the Pascal identity. And the next one is the binomial theorem. Okay. So the binomial theorem is for integer n, positive integer n, let's say, x plus y to the power n can be expressed as the summation of a lot of terms. Each of the terms is of the form x to the power n minus r times y to the power r. But how many of them? For this particular case, there are n choose r of them. So why is it true? So in order to get x plus y to the power n, we can think of, we have x plus y times x plus y, there are n of this bracket sum multiplying together. So we have x plus y, and then another x plus y, and then another x plus y, and so on and so forth. And then the product of these terms can be found out by looking at different choice that we are making to get a term. So for instance, we have x plus y multiplying together. By choosing x in each of the term, we will get x to the power n. By choosing x and then y and then x in all the remaining term, we will have x to the power n minus 1 times y. And then the total formula, the complete formula will be, we need to count how many ways that we can get x to the power n, how many ways that we can get x to the power n minus 1 y, how many ways that we can get x to the power n minus 2 y squared, and so on and so forth. And it turns out that the number of ways to do so, if I want to have exactly r y's, I will need to select which of these n bracket term I'm going to choose the y term. So there's n choose y. Sorry that I didn't have a drawing here, but then I hope you can understand what I'm saying. If not, then also please visit the OCW recording for details. And the final, okay, so these are some examples that you can try. And the last one is Vandermon's identity. So Vandermon's identity is Cn plus n choose R can be written as the summation of a lot of terms, but then each of the term is Cm R minus k multiplied with Cn k. So it looks rather complicated, but it is not. It is very easy to understand. So what does this term mean? So this term, you can imagine that there are n boys, there are n girls. So altogether, there are n plus n people we have. We want to select R people out of these n plus n people, okay? M distinct boys, n distinct girls. How many ways to select R persons, R people from them? Okay, we can count this value. So this is n plus n choose R. So this is one way of counting. This is a direct way. But then we can also separate the counting of this case into finding out how many boys are there. And then we count the number of ways for each of these cases. So there can be 0 boys. So if we don't have any boys, so the number of ways will be, we need to select all the R people from all the girls. So there will be Cn choose R, n choose R, okay? And then there could be 1 boy. So 1 boy means that I have n boys that we can have, and then I'm going to select 1 boy here, and then, 1 boy here, or R minus K boys here, whatever. And then I will need to have, let's switch it a little bit. Let's count for the girls, okay? So maybe we have exactly 1 girl. So in that case, we need to select out of these n girls, which one we are going to pick up. And after that, we have n boys, and then we need to select R minus K of them. So R minus 1 of them. So this forms the case that we are selecting exactly K girls and then exactly R minus K boys. Using rule of thumb, we sum up all these cases because they do not have any overlapping, and they will be covering all the possible scenarios. So in that case, the summation of this one will give this one. Okay, so this is the so-called Vandermon's identity. The proof, if you are using combinatorial arguments, is super simple. You just make up a story and then argue by logic that it is correct. If you use algebra, if you go back to the expression, the formula for CNR, and then plug in here and there, then you will find that it is really very hard to do the simplification. And then, this is a very challenging question, okay? So we want to find out what is the summation of n choose k square. So for instance, n choose k is the term inside this binomial, the Pascal triangle, right? So for n is equal to 3, the n choose k term could be 1, 3, 3, 1. When n is equal to 4, the n choose k terms could be 1, 4, 6, 4, 1. And then what we are going to do here is we are going to square each of the terms and then add them up. We want to find out what is the value of them. So it turns out that if you know the Vandermon's identity, it is going to be easy. We can somehow change n choose k, one of these n choose k, into n choose n minus k. And after that, this is the standard form in the Vandermon's identity. And this is going to be equal to 2n choose n. Okay, that's all for what I want to show you. And then we will have assignment questions for you soon. Yeah, and then we will have our tutorial next week and exam 2 the week after next. Okay, for exam 2, the topics that we are going to cover will be the induction, the Peachono principle, and this counting part. Okay, yeah, good luck. Thanks all for today. Thanks all for coming. Okay, so I'm going to end the stream. Are there any questions? Yeah, if not, then let's end the lecture summary today. Thank you very much. Thank you.